Greetings. I recorded this lecture, and I didn't record this lecture. I recorded it while I was giving it in class, but it turns out that I hit the wrong button and I didn't record it. So I'm going to take this lecture and I'm going to redo it a cappella. I will be on my own with no audience. So let's see how we do here. I'm going to go to the slides first of all, and I'm going to first of all close the slides, and then I'm going to open them. Okay, I'm going to close the slides. The reason I'm going to close the slides is I have notations on there from the last class, and I don't want to have the notation as I start out here. So let me go ahead and open these slides. And yeah, it looks good. Okay, so I'm going to start sharing my screen and go ahead and start the lecture. This lecture is chapter 5 of the book. I suppose I need to share my screen, don't I? Yes, I do. This lecture is over chapter 5. We've completed chapter 2, which has the fundamentals of Fourier analysis. And I hope as we get into some of the applications of the Fourier analysis that we see a great beauty in what happens. When we apply Fourier analysis to real world problems. The first thing we're going to explore in chapter 5 is a review of the sampling theorem, maybe given it a little bit more interesting, I hope more interesting format than you might have seen before. So let me go full screen here. Since I'm doing this solo, I can make myself bigger. How about that? Okay, so this is chapter 5 of my book, Handbook of Fourier Analysis and its Applications. Here is the sampling theorem, and I think everybody has seen the sampling theorem as an undergraduate. It says that we take a signal and we can sample the signal at individual samples. We can sample the signals at individual samples, then multiply them by a sinc function, and we can interpolate them to get the original signal back. Not to a good approximation, but in the spirit of the sampling theorem, exactly. And that's frankly incredible if you think about it. Here are some key events in the development of the cardinal series. I think they're key events because these are people that discovered the sampling theorem independent of each other. There's the old question of whether mathematics is discovered or invented. And we see in many cases in history where the same mathematics is independently generated by 2 or more people. We see this all the time. And we'll see this with the sampling theorem. Other examples are numerous. Principal component analysis was first called the Carhoon and Loew expansion out of 2 people that discovered it independently, Carhoon and Loew. Later on the course, when we get to alternating projections onto convex sets, we'll find out that there's a Populus-Gershberg algorithm. And guess what? Populus and Gershberg both founded the same algorithm independently of each other. And for a while, there was a little bit of back and forth as to who discovered it first. And it turned out that Populus won. He was able to substantiate that he was the first to show the so-called Populus-Gershberg algorithm. In the course of information theory I teach, in algorithmic information theory, we have discovery by 3 people, Kolmogorov, Chaitin, and Solomonov, all independently discovered this idea of algorithmic information theory. So therefore, we see evidence, at least, that mathematics is discovered and not invented. This is a philosophical argument, one that we won't get into, but I think it's it's an interesting topic that people of good will can talk about. So let's talk about the key developments in the cardinal series. First, Lagrange supposedly derived the sampling theorem for the special case of periodic band-limited functions way back in 1765. In 1841, Cauchy recognized the Nyquist rate. In other words, the Nyquist rate is the rate where you have to sample a band-limited signal to assure that the reconstructed signal has no aliasing. A gentleman, H.S. Black, and you can see it's reference 119 in the text, he credits Cauchy for the recognition of the mechanics of band-limited signal sampling, and this was in 1841. So this goes back a long time. He even offered a translation from Cauchy's original French contribution. He said, if a signal is a magnitude time function, and if time is divided into equal intervals such that each subdivision comprises an interval of t seconds long where t is less than yada, yada, yada. He goes on and he basically says that, yeah, if you have a band-limited signal, that you can construct the original signal from sufficiently closely spaced samples of the signal. Now, this remained unchallenged for a long time, that Cauchy was one of the prime movers of the sampling theorem, until a sampling theorem mathematician historian, Higgins, came along. And Higgins said, you know what, I looked up this reference that Black gave, and nothing's there. I don't know where this quote came from. So the discovery by Higgins kind of cast Cauchy's contribution in question. I don't think there's any way that Black would have phonied up the quote that we see here, but clearly he referenced it incorrectly. And I know of no one that's found the quote that Black credits Cauchy with. So Cauchy's contribution is a little bit questionable, but that's life, I suppose. Okay, we go on, and in 1897, we have Burrell's recognition of the feasibility of regaining a band-limited signal from its samples. Burrell is a great mathematician. We use his concept of Burrell's Law all the time in arguing things from a point of design. Burrell's Law basically says if something becomes so improbable that it becomes impossible after a while, if the probability is too low. There's a chance that if you're sitting in a chair, or there's a chance that I'm sitting in my chair, that I will partially tunnel in a quantum mechanical sense through part of the chair. Is that going to happen? No. The probability is so low that we can deem it as being impossible. So this is an example of Burrell's Law. When things become too improbable, we can announce them as impossible. Well, Burrell had recognition of the feasibility of regaining a band-limited signal from its samples as early as 1891. And I believe that these were independent of each other, that Cauchy's recognition, at least the way it was originally credited by Black, is independent of Burrell's recognition. Here's Burrell's quote. Suppose that we have this quote here. And you notice, not this quote, but this equation. You notice what this equation looks like. This equation looks like kind of a Fourier transform, doesn't it? So, and we have a band limitedness in the sense that we have just a band limit from minus pi to pi. And he goes on, and he says the function satisfies the conditions of Dirichlet. We haven't gone over Dirichlet here. Dirichlet was a student of Fourier, and he got a little bit more into the rigor of Fourier analysis and his mentor's Fourier transform or Fourier series work. And he came up with sufficient conditions for the Fourier series to exist. So you don't have Fourier transforms or really weird functions. Like think of the sine of 1 over t. Okay. Sine of 1 over t goes like this. And as we get close to the origin, we have oscillation all over the place, right? And in fact, if you just go through a little epsilon neighborhood here, there's an infinite number of oscillations in this little interval here. And so it's a really weird function, right? And it turns out that this doesn't pass the conditions of Dirichlet. We don't come up against many of these sort of weird functions in engineering applications. So that's the reason that I chose to ignore it here. but this was the observation of Burrell and his imposition of the conditions of Dirichlet in basically stating the sampling theorem. This one, unlike Cauchy, is substantiated quote. So we go on. We have Burrell's recognition of the sampling theorem from its samples right here. And then the first modern interpretation of the sampling theorem was E.T. Whittaker's published work, which got a lot of recognition at the time. Some of these other contributions were less known. Whittaker was interested in something he called the cardinal series. He says, what kind of functions can we look at, take samples from, and then regain the original signal from the samples? And the conclusion that he came up with was basically the sampling theorem. And so that was Whittaker's idea. Nyquist was an employee of Bell Labs, and he established the idea of the time bandwidth product while he was working for Bell Labs. The time bandwidth product, which we'll discuss, tells how many samples that you have to take of a signal in order to characterize the signal to good accuracy. Then along in 1929 came J.M. Whittaker. Now J.M. was the son of E.T., and E.T. does not stand for extraterrestrial, but J.M., I don't know what it stands for. J.M. was the son of E.T. and carried on his father's work. And he was the first one to term the sampling theorem expansion as the cardinal series. And sometimes you'll see this referenced in the literature, the sampling theorem referenced as the cardinal series. And then as we see again, another independent derivation, a Russian scientist named Kotelnikov in 1933 published the sampling theorem. Now at this time there was the communists had taken over in Russia, and I guess there was a degree of secrecy, so it wasn't clear that his publications were popularized in the United States very much. Then probably in the most celebrated interpretation or derivation of the sampling theorem, we have Claude Shannon, who published a classic paper in 1948. Shannon's paper laid the foundation for information theory. And it was the first paper, for example, that used the word bit, which we know today as a binary digit. So bits and bytes, the idea originated from Shannon's original 1948 paper. Shannon also showed that one could communicate with arbitrarily low signal distortion over a noisy channel. It was an astonishing result. He only showed that you could do this, and it wasn't, I believe, until 1990 that somebody actually came up with a way of doing it. Shannon showed it was possible, but it wasn't until 1990 that somebody came up, I believe it was 1990, somebody came up with something called turbo codes, which approached the Shannon limit, the limit that Shannon had set for communication across a noisy channel. And today we use Shannon's stuff in our cell phones to communicate. And that's the reason your cell phones work, whether it's a clear day out or whether it's raining and thundering and lightning, you still get your perfect image over your channel, even though you're communicating over a very noisy channel. Today, I have heard the sampling theorem referred to as the Whittaker, Shannon, Kotelnikov sampling theorem. There was a Stanford professor in Fourier optics that referred to it as the Shannon-Whittaker Kotelnikov sampling theorem. The professor was Joe Goodman. His book was Introduction to Fourier Optics. One of the things that Shannon did, which was really remarkable, is kind of a footnote, kind of a side idea. He says, well, we have to have the sampling theorem. This was in the book that established communication we use on our cell phones and coined the word bit. And he did this in order to show that continuous signals could be digitized into discrete time signals. And the reason he did this was because his theory was all based on discrete signals. And most of the world at that time was dealing with continuous time signals in communication, for example. One was dealing with analog continuous time signals. And Shannon had to build a bridge between the ubiquity of continuous time signals all over the place and discrete time signals, which is what Shannon dealt with. So all of these dealt with either derivation of the sampling theorem independently or polishing the sampling theorem in some sort of sense. Many of the cases where the sampling theorem was discovered, we find out that this discovery was done independent of the other people that derived the sampling theorem, which leads one to believe that, yeah, maybe mathematics, at least in this case, is discovered instead of invented. Now we get with generalizations of the sampling theorem. We have in 1959 Kramer generalizing the sampling theorem to functions that are band limited in other than the Fourier sense. It turns out that there's a number of different transforms. We're going to be dealing later on in multidimensional signals with Hankel transforms. We have Hilbert transforms. We have Z transforms, for example. And some of these have the equivalent of a sampling theorem associated with them. And Kramer generalized the sampling theorem to cases of other transforms that weren't the Fourier transform. So he did a generalization. There was also another generalization, which was done in 1962 by Peterson and Middleton. They were the first to extend the sampling theorem to higher dimensions. And we're going to be studying later on in the course, as we get into multidimensional signals, we'll be studying the work of Peterson and Middleton. It's very ingenious, very nice. And then in 1977, there was a beautiful generalization by Athanasius Papoulas. He's one of my heroes. I met the guy once. When I was at the University of Washington, we invited him up for a sequence of lectures, and he was just a delightful man, but a genius in Fourier analysis. One of the things that happened after Shannon published his 1948 paper is people looked at the sampling theorem and says, how can we generalize it? Well, suppose that instead of sampling it at these sufficiently closely spaced intervals, which we'll call Nyquist intervals, suppose we sample the signal as its derivative, waited 2 intervals, sampled the signal as its derivative, waited two more sequences and sampled the signal in its derivative. And what if we did all that? Turns out that the density of samples that we had would remain the same, but could we generate the original signal back from these samples? And the answer was yes. So that was kind of derivative sampling. And then also, what if we take a derivative or a signal, a derivative, and the second derivative, waited 3 intervals, the signal, the derivative, and the second derivative, et cetera, et cetera. And that was another generalization of the sampling theorem. Another one was non-recurrent uniform sampling. What do I mean by that? You take maybe three Nyquist intervals, and you do something like sample, sample, sample. Then you go over here and you do sample, sample, sample. Now these are not uniformly spaced samples, but they are samples which are uniform, and in each 3 intervals they're exactly the same. But can you restore the original signal with this recurrent non-uniform sampling? And somebody generalized the sampling theorem to show that indeed that was the case. Now this is really interesting because there's all these generalizations. Papoulas came along and he gave one beautiful sampling theorem. I think it's a beautiful sampling theorem, which generalized all of these sampling theorems into one package. And this was his generalization of the sampling theorem. So as it says here, a number of previously published extensions are shown to be special cases. So this is the history of the sampling theorem. And then lastly, I got to blow my own horn. In 1991, I was the first one to publish a book totally dedicated to the sampling theorem. So you see why I'm really passionate about the sampling theorem. I've one time in my life, I studied it very, very closely, at least enough to write a book about it. Book is still in print on Amazon.com. Go buy a copy. And no, don't go buy a copy. It turns out that the Handbook of Fourier analysis that we're using for a text in this course contains much of the material in this book. But nevertheless, it was the first book dedicated entirely to the sampling theorem, 1991. So let's continue with the history and some of the definitions, at least in the parlance of the mathematics of Fourier analysis that we have looked at. We say that a band-limited signal is, or a signal is band-limited if its spectrum can be written as shown here. Now, what does that mean? Well, it turns out that we have a spectrum, and it has a bandwidth of B. So it goes from minus B to B. So we have this spectrum here. And this is the X of U. So the spectrum is totally outside. Well, totally outside the spectrum. The value is equal to 0. So therefore, we only have to talk about the values of the function between minus B and B. This can be thought of as taking the original function and multiplying it by a rectangle function. We multiply it by a rectangle function, and we get the same thing. So this is the pi of U over 2B, if you will. So because of that, we can write the inverse Fourier transform instead of from minus infinity to infinity, which normally is what you use on the interval of the inverse Fourier transform, and instead just integrate from minus B to B. Why? Because outside of this interval, this function is totally equal to 0, and nobody cares what happens out there. Notice something interesting. This is kind of cute, okay? Suppose we take this equation 5.1 here, and we inverse transform it. We get x of t is equal to x of t convolved with the inverse Fourier transform of this rectangle function, which turns out to be, using the scaling theorem, 2b times the sinc of 2bt. This is kind of weird. Does this mean that we can take an arbitrary function that's band limited, and we can convolve it with this sinc? We know the sinc looks like this. And we get out exactly the same signal? We know if we convolve with the delta function, we get back exactly the same signal, but a sinc, we multiply by convolve with the sinc, we get back exactly the same signal. Yeah, it's a very curious relationship, but indeed we do get back the original signal. So here we have it. Here is the, again, the history. This is the definition of the band-limited signal that we just talked about. Here is the inverse Fourier transform for a signal which is band-limited with bandwidth B. And then from this follows the cardinal series. And that is kind of the history. Now we want to fill in some of these gaps and show how the cardinal series emerges from the concept of being band-limited. Before we do that, let me show you what I think is just a beautiful interpretation of the sampling theorem. The sampling theorem says we take the samples and we multiply them by the sinc of 2bt minus n. Okay, so we have these samples here. Let's take the sample here. This sample here is multiplied or weighted, if you will, not multiplied, but weighted by a sinc. So this sample in the cardinal series in the sampling theorem gives rise to this sinc that you see I'm kind of outlining here with my red dashed line. Do you know, remember we said that the sinc went through zeros at uniform intervals? And that I think that the sinc of n was a Kronecker delta of n because all of the zero crossings were at 0. Well, this is beautiful here because this sinc comes down, and guess what it does? At the point of the next sample, it goes through 0. So this sample will make no contribution to the interpolation at this point. That's kind of cool. And it goes down, the sink goes down, and it comes up and it goes through the zero crossing of the next sample point. So you can see when you interpolate, it isn't clear how things are filled in, but because of these sinks and because of the zero crossing, we know that whatever the interpolation is, it's going to pass through all of these points. And that's because of the beauty of the sink function and the fact that the sink function passes through integer or passes through zero values at periodic points. And the sampling theorem places those points so that the contribution at a single point gives no contribution to the interpolation at any other point. That's a beautiful, I think, geometrical interpretation of what's going on here. Okay, with this now, I'm going to give what I believe is an incredibly intuitive explanation of the sampling theorem. It's going to be based on some of the theorems that we had. Hopefully, we're beginning to think in terms of theorems and some of the properties that we have. Some of the properties of different functions, like a comb Fourier transforms to a comb, and we'll use a rect Fourier transforming to a sink, etc. So we're going to start out with number one here. Number one says that, okay, we have a band-limited signal and x of t, and here's the double arrow denoting a Fourier transform pair, and that's going to be band-limited between, say, minus b and b. So that's what we start out with. Okay, here's what we're going to do. First thing we're going to do is multiply a comb by a comb function. Why do we multiply by a comb function? Because that comb function multiplied by the original function just gives us the samples of the original function. So right now, don't pay any attention to the left, just pay attention to the right. I'm sorry, don't pay any attention to the right, pay just attention to the left. Pay attention to what's happening in time here, because that's what's happening intuitively. Intuitively, we're taking a signal and we are multiplying it by this comb function. And what happens is when we multiply it, every place this is zero, it's going to zero out the original signal. And everywhere there's a delta function, that's going to be weighted by whatever the value of the original function is here. So in kind of an abusive notation, because delta functions are infinitely high and zero width and have a finite weight, but we usually schematically represent them by arrows. And the longer the arrow, the greater the integral under the delta function. So we have this original signal here, and that original signal turns out to be the envelope down here, but we don't have the original signal. We just have the samples of the signal, the samples being the weights of the Dirac deltas here, if you will. So this is all well and good, and it's very intuitive. What happens that is not as intuitive is over here in the frequency domain. So we're going to follow this over here. Here we're multiplying by a comb function in order to get this signal of samples. That's what this is, a signal of samples. What happens in the frequency domain? Well, if we multiply in the time domain, we convolve in the frequency domain, don't we? And we know that the Fourier transform of a comb is a comb. So we are going to be convolving this function with a comb. And we know because of the way the Dirac deltas work, we're going to get that spectrum centered everywhere there's a Dirac delta here. So we're going to have a periodic replication of the original spectrum. And this periodic replication is going to be the Fourier transform of the sample. So interestingly, if we sample fast enough, we get a periodic replication of the original signal here. And guess what? This original signal here lives on. Except it lives on as a single period of a periodic signal. So that in itself is kind of cool. Now, of course, you have to sample fast enough. And I think you recall from the sampling theorem, if we don't sample fast enough, we do what? We alias. And we'll talk about aliasing in a little bit. So that's well and good. We find out intuitively by sampling over here to the left in time that we replicate the original spectrum as shown here on, I'm sorry, on the left we sample, on the right we do the replication of the spectrum. Now our job is to get back the original spectrum from this duplication. And we do that by multiplying by a rectangle function. So here is this duplication. And over here, we did things intuitively in the time domain. Now we're going to come over here and we're going to do things intuitively in the frequency domain and find out what its ramifications are in the time domain. In the frequency domain, we get back the original spectrum, low-pass spectrum, by taking this periodic signal and multiplying it by a rectangle, right? So we multiply it by a rectangle and we obtain the original spectrum back. This is all well and good and very intuitive, right? Remember, the intuition up here is in time. The intuition over here on the right is through frequency. Well, let's see what happens in the frequency domain, which is not as intuitive. We're going to multiply by a rectangle here to get the original signal back. Well, if we multiply in the frequency domain, what do we do in the time domain? We convolve, don't we? And just like before, we get this sinc function replicated everywhere there is a delta function. And it's going to be replicated in such a fashion that it has a height equal to the value of the sample at that point. So we're going to see what we had before, what I showed you before. In other words, this sinc is going to come down. It's going to go through all the zero crossings. And then we're going to have another sinc, which is here, which is the replication here. It's going to go through all the zero crossings. And then we're going to have one here. And you add up all these sincs, and guess what? You get the original signal. How do we know? We know because it happened in the frequency domain. And if it happened in the frequency domain, it has to have happened in the time domain. And so this is the relationship that we get. And this is a kind of an intuitive geometrical explanation of the sampling theorem, and I think is a very clean way to think about the sampling theorem intuitively. Now, you notice that we haven't gone into the detail of the equations here, and I want to do that next. And once we have this geometrical idea in mind, we can go through the equations relatively quickly. So let's go ahead and do that. Let's first of all start out with step number 1. And you'll notice here that the steps are numbered. This is step number 1. Step number 1 is to get the signal of samples. This is the original signal times the comb function. Now the comb function is a bunch of Dirac deltas. And they are going to multiply the original signal and only give us the samples of the signal, right? And so this is the way that we can think of and talk about the signal of samples. And on the right here, let's see what happens on the right. On the right, we know that this comb Fourier transforms to, in the frequency domain, to another comb. So over here we have the signal of samples is equal to x of t times a comb. In the frequency domain, it's equal to the convolution, because you multiply in one domain, you convolve in the other domain. So it's equal to the transform convolved with the transform of the comb, which itself is a comb. And doing so gives us this, this periodic duplication, doesn't it? Okay, so this is what takes place as we go down the time domain here, which is the intuitive part, and then go over here to the frequency domain and do what is the consequence of what happened in the time domain. Okay, next step now. We've gone through steps 1 and 2. The step number 3 is taking the original signal, multiplying it by a rectangle function, appropriately scaled, 1 over 2b, and giving us back the original signal. So I don't have any place for my beautiful, beautiful picture. Let me put myself up here. So we get x of u is equal to s of u, which is this function. the S of u times the rectangle function. And I don't know where all my stuff went to, but it's here in spirit. And that gives us the rectangle function here. I'm sorry, the rectangle function gives us the original spectrum. This is very intuitive, as long as the signal is not aliased. And let's see then what happens in the time domain. In the time domain, which is step number 4, multiplying in the frequency domain corresponds to convolving in the time domain. So x of t, if x of u is equal to s of u times this rectangle function, then its inverse transform is going to be s of t, the inverse Fourier transform of this. This is the signal of samples, convolved with the sinc of 2bt. So that is what happens on the right. And this is step number 4, if you will. And here's the cool part. Here's s of t. We can go back up here and grab s of t as this point, as this equation, and we convolve something with sinc of 2bt. We're convolving it with these delta functions, and so for every delta function, we're going to get a sinc, and guess what? That sinc is going to be weighted by the sample of the signal at that point. And there we have the sampling theorem in all its glory. In terms of a very intuitive approach via the geometry of what happens in Fourier analysis and some of the theorems and Fourier transform pairs that we learned. Really, really intuitive. Now, of course, we do know that there is something called aliasing. What happens with aliasing? Aliasing happens when you don't sample fast enough. There's a number of explanations and a number of ways to look at aliasing, but here's kind of a classic example. Suppose that you have a signal, and this signal is this sinusoid, very high frequency. But this high frequency sinusoid is not sampled sufficiently fast. And so it's sampled here, and it's sampled here, and it's sampled here, and it's sampled here. So we're sampling the high frequency sinusoid at a low rate. Well, notice these samples, which are taken from the black curve at a low rate, can also be interpreted as samples from a sinusoid of a very low frequency. Isn't that right? So therefore, we have a problem, don't we? In that we don't know how to interpret these samples as samples from a high frequency or a low frequency. You know, this aliasing, of course, comes from the duplication. The duplication of the spectrum such that there's overlap. Now, it doesn't mean, this is S of u from our previous slide, it doesn't mean that everything is bad and lost, especially with this, which is called first order aliasing. I'll talk about second order aliasing in a minute. Think, for example, of a duet between a flute and a tuba. We know that the flute is high frequency and the tuba is low frequency. So on the band, if we were to look at the band of a flute and a tuba, we would say that the tuba might be down here. These are audio frequencies. And the flute might be up here, right? Here's the tuba. And the flute, of course, has a higher frequency. So it could be that in the alias spectrum that the tuba part of the spectrum remains unscathed. And it's only the high frequencies that get aliased. We can see that in the previous slide that we looked at, where that high frequency sinusoid manifests itself as a low frequency. So yeah, that's clearly a problem. So we can actually regain the tuba, okay. Another thing we can do is figure out what the integral of a signal is. If you're interested in such things, remember that x of 0 is equal to the integral over t of x of t dt. This was the integral property of Fourier transforms, which means that if you have a Fourier transform of a bandlimited signal, say from minus b to b, and this is u, then the value at the origin, where'd everything go? Okay. I don't know where everything went. I got to learn to use this stupid pen. Okay, let's try it again. The integral well, isn't that interesting? I'm going to have to go over here. That the integral over t of x of t is equal to x of 0. So my point is that if you have an x of u, that the value here is equal to the area under the signal. Notice that if we have an aliased version of the spectrum, that this point is still accessible to us, isn't it? So even if we have alias data, we can still compute things like the overall integral of the signal, can't we? But this is only true for first order aliasing. We can have higher order aliasing. Higher order aliasing occurs when sampling is so slow that not only the first replicated spectrum, but the second replicated spectrum comes in and overlaps the first order spectrum. And of course, this is going to be, let's see if I can do this righteously. So we're going to have this sort of thing. And you'll notice for second order aliasing, second order aliasing, the DC value is totally eradicated. So we have no idea what's going on. But for first order aliasing, we can recover the original signal exactly. So that's kind of cute. So what I want to do is I want to show you a video here. I think I want to show you a video. Maybe I have to want to keep my ink notations. No, I don't want that. Oh, okay. I don't understand what was going on. I'm still trying to use this stuff, guys. So thank you for your patience. I want to go here to an internet connection and show you something. Let's try Firefox. This is a demonstration on Firefox of something called the Wagon wheel aliasing. Many of you are probably too young to remember old Westerns where there was a stagecoach with a big wheel and spokes in the wheel. And as the stagecoach started to go away, it looks like the wheel was literally turning backwards. That's the reason they call this the wagon wheel effect. Here we have a case where we have periodic replications, and these periodic replications are much smaller here, they're a little larger here, and they're very large here. So the periodicity in this case is not once per rotation, but just the distance between one black area and the other black area, if you will. And that's a replication. Now, the aliasing here is going to be caused by a camera that is operating at a frequency that that is not sufficient to capture the true the true rotation. And it turns out that the camera might take a picture here, wait for the rotation, not here, but maybe this thing goes over 2 or 3 in a little bit, and it really looks like that aliasing problem that we saw with the sinusoid exactly. So this is a beautiful representation of the concept of aliasing. You can see we get the aliasing and we get the slowing down because we're not sampling sufficiently closely to make sure that as one black thing moves to another black thing, that we get a couple of intermediate results in there. So this is an example called the wagon wheel effect, as you can see, where we get really weird cattywampus aliasing effects. Okay, next time, we're out of time here right now, but next time we're going to give you another proof of the sampling theorem. And this is really interesting. We've seen that everything in Fourier analysis has a duality. If we have a dual of something, then if we have a Fourier transform, we can always apply the duality theorem and get another Fourier transform. If we have a Fourier theorem, we can apply duality and get another Fourier theorem just by switching the time and the frequency domains. Well, the sampling theorem has a dual. Yes, the sampling theorem has a dual, and it's a dual you're very familiar with. And we'll show this next time. And we'll show that the Fourier dual of the sampling theorem is nothing more than the Fourier series. In fact, Shannon, in his original 1948 paper, derived the sampling theorem using the Fourier dual of the Fourier series, and basically showed that result. So until next time, be of good cheer, and we will talk to you then.